Hello! In this video, we are going to prove the following theorem. The sum from k equals 0 to infinity of z to the k over k factorial converges for all complex numbers z. Now in proving this theorem, we are going to use the following preliminary result. We have proven that the sum from k equals 0 to infinity of x to the k over k factorial converges for all real numbers x greater than or equal to 0. Right? The way we proved this was we proved that the sequence of partial sums is an increasing sequence and that it's bounded above. Right? And that proved that the infinite series converges. But now, using this fact, we are going to prove that the infinite series converges for every complex number. So, to start out the proof, let's first give ourselves an arbitrary complex number, z. And from here, we want to show that this infinite series converges. Well, what does it mean for this infinite series to converge? Well, it means the following. To say that this infinite series converges means that this sequence of partial sums converges. And here I'm choosing a starting index of 1, and it really doesn't matter what starting index you choose. I just like to choose a starting index of 1. But remember, a sequence of complex numbers is convergent if and only if the sequence is Cauchy. So, to show that this infinite series converges, all we have to do is prove that this sequence is Cauchy. So then, what does it mean for this sequence to be Cauchy? It means for every epsilon greater than 0, there exists a positive integer, capital N, such that for all n greater than or equal to capital N, and for all positive integers p, the absolute value of the n plus pth term of this sequence minus the nth term of this sequence is less than epsilon. Right, so this. Now let me write down that our whole goal is to prove that this sequence is Cauchy. And to prove that this sequence is Cauchy, all we have to do is prove that this statement is true. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a positive integer such that this is true. Now, remember, we know that this infinite series converges for every real number greater than or equal to 0. Well, in particular, we know that the absolute value of z is greater than or equal to 0, so let's just take x to be absolute value of z. Right, so we know that this infinite series converges. But just like the chain of equivalences we established here, to say that this infinite series converges is equivalent to saying that this sequence of partial sums is Cauchy. So since we know that this infinite series converges, this means we know that this sequence is Cauchy. What does it mean for this sequence to be Cauchy? It means precisely this. It's just instead of z, we have absolute value of z. So we know that this statement is a statement about every epsilon greater than 0. So in particular, it must work for the epsilon that we have in our proof. So because this sequence is Cauchy, we should be able to find a positive integer capital N, such that for all n greater than or equal to capital N, and for all positive integers p, the absolute value of the n plus pth term minus the nth term is less than epsilon. Now remember, the whole goal has been to find a positive integer such that this statement is true? Well, the claim is, if we take this positive integer to be the capital N that we have in our proof, then this statement will be true. So taking this positive integer to be the capital N we have in our proof, we proceed to prove that this statement is true. Well, since we're trying to prove a statement about every integer greater than or equal to capital N and every positive integer, let's give ourselves an arbitrary integer greater than or equal to capital N and an arbitrary positive integer. I'll call them N and P. From here, we are going to show that this inequality is true. So let's start out by writing the left-hand side. Now, as you can imagine, this sum is essentially contained in this sum. So what we're essentially doing here is we are taking away everything from k equals 0 to n in this sum. And we're left with the sum from k equals n plus 1 to n plus p of z to the k over k factorial. Right, just like that. But then we can apply the triangle inequality, which tells us that the absolute value of a sum is less than or equal to the sum of absolute values. But then we know that the absolute value of a fraction is equal to the absolute value of the numerator over the absolute value of the denominator. And then we know that the absolute value of k factorial is just k factorial. And another property of absolute values tells us that we can move the k to the outside of the absolute value. So we get this. But then, just like we did right here, we know that this is the same thing as the sum from k equals 0 to n plus p minus the sum from k equals 0 to n. But remember, this is a real number, and every real number is less than or equal to its absolute value. Right, just like that. In fact, this guy is actually equal to its absolute value because this sequence is an increasing sequence, right? Which means every term in the sequence is less than or equal to the term that comes after it. So since this term comes later in the sequence than this term, well then this guy must be greater than or equal to this guy. And so this guy is greater than or equal to 0, which means this is equal to its absolute value. Right? But now, let's use the fact that this statement is true. Right? This statement works for every integer greater than or equal to capital N and for every positive integer. So in particular, if we take n to be the n we have here, and we take p to be the p we have here, well then we have that this inequality is true. So this guy is less than epsilon. And so we have shown that this guy is less than epsilon, which is exactly what we wanted to show. And so we have proven that this statement is true, which proves that this sequence is Cauchy. But from the chain of equivalences we discussed earlier, we know that this is equivalent to saying that this infinite series converges. And so this completes the proof. And so we've proven that this infinite series converges for all complex numbers z. Now for each complex number z, we're going to define the value of this infinite series to be the following. We define the value of this infinite series to be e to the power of z. And so, yeah, that's pretty much it for this video.